Hey everyone, just wanted to welcome you to week 2 of ME 124 Lab. So this is going to be your second lecture, and in this lecture here we're going to cover the material that you'll be working on in your first lab, Lab 1A, the Photoelasticity Lab. So if we look back at our schedule that's posted on Blackboard, we can see here that now we're entering week 2 starting on the 7th. And again, the lecture material here that's going to be covered is going to be Lab 1A. Your actual first lab, Lab 1A for Photoelasticity Lab, won't occur until next week, the week starting the 14th. So always reference back here and you can see what weeks you have lecture and which weeks you have lab. So if you have, depending on which mode you signed up for and which section you signed up for, which we can reference up here, will determine which lab you attend and what time and which mode you attended in. So if you signed up for Lab A01, that's going to be on Mondays from 10:15 to 11:45 in person. If you signed up for Lab A2, this is in person as well, and that's Mondays from 12:15 to 2 o'clock. Lab A3 is 10 o'clock to 11:45 on Wednesdays, and Lab A4 is 12:15 to 2 o'clock on Wednesdays. And again, all these labs, A01 through A04, are all in person. That's the mode you signed up for. If you signed up for the online version, we'll be posting these to Blackboard for you. So as we move into the material that we'll be covering in this lab, our technology we'll be dealing with is photoelasticity, taking a look at the theory of polarized light, photoelasticity, and material loading and beam bending. So as we discuss light, one of the topics we're going to look at is electromagnetic waves. So we have an electric field E and a magnetic field H. Things are being moving at the speed of light, which we denote as c, and the wavelengths we're dealing with here are between 400 and 800 nanometers. So here's our wavelength down here. We have our amplitudes, we have our velocities over here along a z-axis. So if we're thinking about light and air, which is typically what we're going to be dealing with in these labs, we have c is equal to our velocity, our v, of 3 times 10 to the 10th in units of centimeters per second. So slower in other materials, depending on material, the speed of light will change. And we can talk about our index of refraction. So we have an equation down here for index of refraction. N1 is going to be used for the variable denoting for index of refraction is equal to the speed of air divided by the speed of material. We're talking about variable material V over V1 here. So V1 would be the material. So here we have a diagram on the right. Here's our light moving through air at wavelength here, velocity here. As it goes through some medium, whatever material we're dealing with here, has some V1 velocity. Then we go back, once it leaves the medium, back into air again here with a V. And again, now we look at our index of refraction here. For air, it's N. For our medium, it's N1, which is what we have down here. So these indices of refraction may vary between different materials. Thickness may stay the same, but the material properties are different. We have a retardant here, delta, is given by this relationship T times N2 minus our N1 over here. We can see T is our thickness of the material right over here. Here's our delta term there. Again, our V's, V1 and V for this type of material up here, but down here we have a different material, even though it's the same thickness, different material, we have a V2 and an N2 associated with that material, whereas in the top material we had a V1 and an N1 associated with it. So now this brings us to the topic of birefringent materials. So certain materials are optically isotropic when unstressed, and they become optically anisotropic when they are stressed. So we'll see different colors change in these, as we can see over here in the right on this. The change in index of refraction is a function of the stress and the strain. So when we're talking about photoelasticity, you can make solid pieces of the same size and the same shape and coat a thin part with a thin layer of this reflectance. You can see this process occurring over here. So now we're going to take a look at plane polarized light. You can use a polarizer to transmit a single wave of light in one plane. So what we have down here in our diagram, we can see here's our light source, but then you have this random emission of waves and vibrations contained in various planes. Well, we can send that through this polarizer here, where some are to be transmitted and some are not. And we come off the backside, we can see this one plane of transmitted light right here. So the transmitted wave vibration in the plane P. So just in one plane. Continue on with this topic of plane polarized light, we can do is add another polarizing filter, uh, either perpendicular or parallel orientation there. Again, the difference being now, if we have this perpendicular orientation here, this is equal to a dark field or extinction, and the parallel is full light or the light field. So this first part of the diagram down below here, we have the light source and coming out in multiple planes right here, goes through the first polarizer, and then as we saw before on the previous slide, it's transmitted into one plane. Then we can go through this here and go through our next polarizer here, and we can get the dark field coming out the other side. So now what happens if we want to add in our test specimen here? So we're going to have some test specimen of a known thickness T here. We're going to have our first polarizer over here, so we have our light source going through this first polarizer. We have our reference angle alpha here. Coming out of this polarizer, we have our polarized light. So this is what's going to enter through our test specimen here, and the opposite side we'll have what leaves our test specimen there. We can go back through this analyzer A over here and get our results coming out of the other side here. So what does this look like in terms of our diagram here when we apply a strain to our sample? Well, if we have the specimen and we apply a strain to it, we start with our strain at 0 and we apply some certain strain to it later. We want to draw these out separately. Here's our strain of 0. Here's our applied strain right here to our material. Some material here in green of some thickness T. So what happens when we do this, we can see, okay, here's our wavelength coming in here. We have a V1. It goes through our medium here, our sample, our specimen, and we can see that this changes to a V1 rather than V, comes back out, and there's our V there. So this is for 0 strain applied. So if we apply some strain epsilon down here, we can see, okay, here's our wavelength coming in from our light. When the polarizer goes through our material here, now we can see we have this V2. This is all in green here, the same material. This is just no strain applied. This is strain applied to it here. So what we can see is that our index of refraction is going to change from N1, with no strain, to an N2 when we have a strain on it. So in this diagram here, we can see that in our principal strain direction, our speeds of light are in components of Vx in the x direction and Vy in the y direction there, and our indices of refraction are in Nx and Ny. So we want to break things down in terms of components, and this is going to be based upon our reference angle that we see here of our beta. So what we can see here in this slide is if we want to calculate our delta, or this distance here, our retardation, we have this relationship over here. So the relative retardation between these two different waves is delta is equal to c, our speed of light, times 1 over vx minus 1 over vy. Now, we also know this thickness here, t, so we can rewrite this equation and say that delta is equal to t times nx and ny, our indexes of refraction. So as we can see in this diagram here, we have the case if the principal strains are not in plane of polarized light, indices of refraction change in two planes. So we can take a look at our diagram down here, light source going through our polarizers, coming out in one plane, going through our specimen here of known thickness here, some reference angle here of beta, comes out over here. We have our delta that we've just learned how to solve for on the previous slides there, and now it comes out through goes through our analyzer over here A. We have our interfering components here, and we can see that there's a resulting phase shift. So now let's take a look at some of our key equations here. The first equation we're going to talk about here is Brewster's law, or our stress optics law. So relative change in the indices of refraction are proportional to the difference of the principal strains. This is given by this relationship shown here. So we have our n sub x minus n sub y is equal to our k term here times epsilon sub x minus epsilon sub y, where k is the strain optical coefficient, similar to our gauge factor. So must be established by calibration, as you will do in Lab 1B. So this is where it kind of leads into why it's important to do the calibration, which we'll be covering in the second portion of the first lab in Lab 1B. So now we have two relationships here. We have our Brewster's law and we have a retardation delta down here. We can combine these two together. If we take a look at Brewster's law here, we can see that n sub x minus n sub y is equal to our k times epsilon x minus epsilon y, whereas in our delta down here we have delta is equal to t times nx minus ny. So we can see that nx minus ny, according to Brewster's law, is equal to k times epsilon x minus epsilon y. So we can take this term right here and we can plug it in right here. So that's what we're going to do, is we're going to take that, plug this in down here. What we end up with now is delta is equal to t times k times now epsilon sub x minus epsilon sub y. Now we can rearrange this and solve for epsilon x minus epsilon y here, and when we do that, we end up with this relationship down here, the basic relation for photo stress analysis, where epsilon sub x minus epsilon sub y is equal to delta over tk. So we end up with this relationship right there. So now if we talk about resulting light intensity here, which we can call I here, this will be a function of our delta, our retardation here, and the difference of beta minus alpha, which are these two angle references here between your specimen and your analyzer over here. So there's your beta and there's your alpha right there. So this, if we take a look at our relationship now, our I, or our resulting light intensity, is equal to b squared times the sine squared of 2 times beta minus alpha times the sine squared of pi delta over our wavelength. So let's take a look at the resulting light intensity for our dark field configuration here. So if we have this relationship for our I over here for our light intensity, we'll take a look at this term here, our sine squared 2 times beta minus alpha. So the light intensity becomes 0 when our beta minus our alpha is equal to 0. Now this occurs when the principal strains are aligned with the polarizer and our analyzer there. Something that we can do when we're dealing with the dark field here is we can add in these quarter wave plates to produce circularly polarized light. So we can see down here, here's our Q1 quarter wave plate right there, and our Q2 quarter wave plate right over here that we've added in. So we can note that light transmission is not affected by direction of principal strains. So we can see down here in our diagram we have our unpolarized light coming in through our linear polarizer. So then coming out of this we have our linearly polarized light going through this quarter wave plate right here, and now we have this left-handed circularly polarized light coming out. So now if we go back to our intensity equation here, again we recall that we have I is equal to b squared times the sine squared times 2 times our beta minus alpha here times sine squared times pi delta over our wavelength. While our angle term does not affect, so we can cross that out. Cross this out here, and what we end up with is this relationship down here where I is equal to beta squared times sine squared times pi delta over our wavelength there. So let's take a look at our dark field configuration. The intensity is given by the following relationship here, where our I sub dark is equal to b squared sine squared pi delta over our wavelength lambda here. So I dark is equal to 0 when our delta is equal to 0, our delta is equal to 1 lambda, our delta is equal to 2 lambda, or our delta is equal to n lambda here, where n is the fringe order. So if any of these cases for delta, we could plug back up into here, and our I sub dark would be equal to 0. So for a given wavelength, our delta is described by the following relationship, that delta is equal to n times our lambda function there, where we have lambda here as our wavelength. In white light, we have this value here of 22.7 times 10 to the negative 6 inches, or 575 nanometers. So we have our strain relationship here that we call from before, epsilon sub x minus epsilon sub y is equal to now our delta over tk. Well, now we have an expression for delta. We can replace delta with our n lambda here. When we do that, we end up with this relationship here, epsilon sub x minus epsilon sub y is equal to n times lambda over tk, and this can be reduced further based upon the relationship that for f right here is equal to our lambda divided by k, so we can plug that in here. So now our epsilon sub x minus our epsilon sub y is equal to n times f over t here, or our fringe constant is f. Now if we take a look at our isotropic birefringent materials, the orientations of the principal strains are the same as the principal stresses. So we have our sigma sub x minus sigma sub y is equal to our n here times our wavelength lambda over tk. Again, this reduces down to n times f sub sigma, where f sub sigma is our fringe constant down here, over t. So any n or band or color shows the portion of the element that has the same magnitude of difference between the principal strains or stresses. So now that we've taken the time to go through and look at the dark field configuration, next let's look at the bright field configuration here, wherever I sub light is equal to the expression b squared times cosine squared times pi delta over our lambda term. So I sub light is equal to 0 when the following occurs: when delta is equal to pi over, or to lambda over 2, 3 lambda over 2, or n plus 1/2 lambda, where n is our fringe order there. Now, one of the devices we're going to be using in this lab is our Opticon here. So we can see this in the diagram here. This is a simple loading device where you can use these little screw inputs here to tighten down and apply a load to specified points on our specimen. So here's an image of the Opticon with an actual sample inside here and some loads being applied. So you can see you have these 4 different screws that we can thread in, turn in, and apply 4 loads at 4 different locations on our specimen here. See, once these loads have been applied here, we can see the colors changing within our specimen here. So once we've applied these loads to our specimen here, we can use this relationship that we saw in the previous slides here, where we have our sigma sub x minus sigma sub y is equal to our n times our wavelength over tk, which reduces down to now nf over t. So let's take a look at our fringe order chart shown here. So we have here on the left, we have our color scheme associated with n equals 0, n equals 1, n equals 2, n equals 3, and n equals 4. Related to our fringe order there, we can see our color scheme here. For each of these colors, we can see we have a corresponding relative retardation in nanometers and in inches times 10 to the 6, corresponding over here to the fringe order n on the right side there. So we can use this chart in order to get information to plug into those equations. Now what we can see here, here's another sample. We've applied these 4 loads at these 4 locations here, and you can see the corresponding colors that we could go back to that chart in order to get the information from. Another sample shown here again. See the 2 loads being applied close up here, and now we can see these colors coming out here, which again we can go back to that same fringe order chart. So this leads us into the actual lab that you're going to be doing next week. So within this lab, there's going to be you're going to need to measure specimens, set up the loading, measure the locations of these load applications, use the light box in order to take pictures with the SLR, and you can use that chart that we just took a look at in order to determine the fringe order. So for the analysis portion of this lab, we're going to need to draw shear and moment diagrams of each loading condition. We're going to observe fringe order spacing relative to cross section. You use your knowledge of normal and shear stress at cross sections in the beams, stress concentrations, etc. You can describe why the fringe pattern is or is not like the theory, and describe what is happening near points of load, applications, and why. So here's another image from the SLR here of a sample where we now have these 2 notches inside of this here. With any of these specimens, one of the things we mentioned that we're going to need to do in this lab is to take measurements, know the overall dimensions. So we can take the information we can see here and the known dimensions and location of these loads. So for our specimen here, we have those 2 notches. We have the known dimensions, thickness, the height, the distance between those 2 notches, the radius of the notches here, which we can measure. We can have this equation here, our sigma is equal to our mc over a, or 6m over bh squared here. Again, there's our h and there's our h and there's our b right there. We can see down here on our x-axis we have our r over h, where we now can get our case of t out of this here, and we choose the curve based upon our h over h ratio from our measured dimensions of our specimen.